Yeah, so welcome back to the second part of Cloud Computing and Big Data, Lecture 4, Virtualization and Data Center Design. So many elements we talked before in the first part were really basic materials of computer science, basically teaching part of operating systems, virtualization, ideas of these different virtualized layers, hypervisors, VM images versus VM instances. They are all important in a way to know. But the deep down details, let's say, of specific hypervisors you have seen, like VMware and Zen and so on, is not so important for you to know, especially not in this course here. But the key idea of this virtualization will be coming back to us when we do infrastructure as a service in Lecture 8, when we do specific VM instances for neural networks in Lecture 6. So you see that this kind of virtualization topic, that's why I bring it very in the beginning. It used to be actually much before, but we entered some more practical topic for assignments for the students based on our feedback from students. That is really something where you see underneath the hood of clouds, virtualization is always present. Here we talk about a little bit related aspects, and we'll go into some of the details more in a larger setup, and also think a little bit about, again, the errors that could happen. What about this economics of scale when we really scale up big? Why we do this? You have seen in the video, hopefully a little bit, that it relates to costs, and we didn't talk about that yet. So let's talk this a bit more in this part of the lecture. So this is a nice area, again, where you would see, this is a typical scenario in a big data center. You would have, let's say, these nodes, which are always put there abstractly up there, which says limitless scaling, a bit into a more realistic setup, right? This is the same picture if you want, more realistically. And you would see the cloud data center, of course, has real CPUs, hardware, physical, right? It is touchable. That's why we also go to Vern and touch some real clusters, so that you see that a cloud is, of course, real. But what's happening is that you don't see that as a user, right? It's hidden somewhere in different clusters. You have seen that in the video and the different lines that they usually have. And on top of it are these virtualized ideas, which brings us to an idea of virtualized clusters. So you can combine now different ones. And of course, you would combine them in a way of keeping the load high, because if you have the physical hardware just idle, not used, you have spent hell a lot of money for buying it, but not using it or operating it. So the power is on and basically the cooling is on and you don't really use it. So it's very bad as well. So hence you see with this kind of virtualization setup, you kind of try as best as you can, not perfectly. You see always here, there will be holes in the schedule. Sometimes people can't use parts because it just doesn't fit to your user load, right? They also want to have, let's say, 60 worker nodes of Spark. That means we need this part of the resources. They maybe just need 20 Spark nodes. They don't use Spark at all. They just use Hadoop. But in the end, the whole cluster setup must match to the physical resources available. And if it doesn't, you will see every now and then these holes. These holes in the schedule are, of course, bad for the data center. It runs the cluster completely, full power, but nothing happens, right? And with this, of course, it turns into money quickly, money unused. Hence, the idea of data centers is always to have it as much utilized as possible, the resources. Now, when you would now assign physical resource 1 decode, physical resource 2 weather store 1, physical resource 2 university, then you will see basically on different loading patterns, there will be lots of idle resources. So that's not how you would do it today. But if you would buy all our own physical clusters, that would work that way, right? By using, let's say, a centralized cloud setup, they can all share in a virtualized fashion those clusters and would reduce the number of clusters and keep them more utilized. And with this, of course, better accessible and all the other aspects you heard in the video. But this is a very key consideration. And in almost all you go in all the cloud, they work basically the same way. And we leverage this as an example here with the Apache Spark. Of course, this goes for all the different applications you will see. And here's an example again, when you have the different virtual machines running, and there's essentially different deployment scenarios, how you can envision this when you have all this network. There's basically nodes for basically an application C that is stretched across different clusters. And the way how it is scheduled and put on different clusters is, of course, done for you. So you don't really go to the cloud and say, I will put it there and put it there and here. Usually you have a system like Yarn and Apache Spark that takes care of these things. When you, of course, be on the infrastructure as a service level and you are a sysadmin, you are basically in that field, then there are some options that you can do this. You have seen in the video, you can also abstract, for instance, from network. You can create your own virtualized network, not only storage and computing, also network. So you can make your special zones and so on that, you get always these parts of the clusters, more or less, in a, let's say, more easy way talked about. But in the end, you have an application load, which is extremely flexible from all these different colors that you see across all the physical devices on the lower, but you don't care about it because it's all virtualized and available to you. Of course, think about it, the more application load you do, the more credit card swipe you have to do, of course, because you use more computing or storage. So this is a kind of application partitioning idea, but there are many different ideas using virtualization. And now when you look where basically virtualization is used in large data centers from the kind of three main ones, Amazon and Microsoft and Google, you will see it's everywhere indirectly combined with virtual storage, with virtual networking, and also virtual compute. They all named differently, right? You have here things like MapReduce, for instance, in Amazon are called elastic MapReduce. And things we learn now in lecture 5 and lecture 5.1 and so forth is also the key consideration for Hadoop clusters, which are very similar like Spark clusters. And they all name them differently, but have very similar ideas how they operate with this virtualized resources. So the names of that is also not so important, but for you, the idea is to think about they all do this with the provider idea of delivering this, but have all very different names for it. Underneath, they're doing almost the same thing. There's maybe a 20%, 10% per service that they do unique. So a unique selling proposition, right? So where I said, in some of the clouds, the Spark cluster doesn't scale automatically, while in Amazon, in Elastic MapReduce, when you use Spark, you can somehow switch auto scaling and it will employ more workers. Of course, there you have to be careful because it will cost then also directly more. Just to take away that essentially the same ideas how to do it would be always employed in these. Now thinking a bit more about the costs, right? This was also a bit in the video roughly. You have here an idea when you do this now as a traditional IT cost model, you would have always this fixed cost in capital equipment. So you would really have the real hardware on your premise, right? Don't forget that this is essentially more or less hardware, mostly equipment, but this can be storage, CPUs, network. Now, what you also have to see, the more of those you have to have more administrators, right? The hard disk will always fail per week. So they have to have someone manually taking out the hard disk. There are no robots, or sometimes there are robots yet now, but mostly you have a sysadmin changing the hardware and reinstalling and doing the node. So the more you basically have here in terms of IT, the more variable costs you have. And it's the sense of people working. And of course, what also comes to the point is you need here and there more cooling, right? You have suddenly a big hall full of computers, and you will realize that actually one of the key challenges today in a data center is the cooling, or the most cost, to keep it chilled. Hence, Iceland, ambient air cooling. That's why people move here, right? And create things like Vern Global and so on. And you find examples in Finland, in Kajaani, it's the same way. It's very much in the north in Finland, while the data center originally operates from Helsinki, but they operate their Lumi HPC center in the data center in Kajaani, very much in the north, because it's very cold, ambient air cooling, and you can save hell a lot of variable costs. Of course, they still have the fixed costs, right? Now, the idea now using cloud computing is different, right? This is more the HPC setup. If you basically go to cloud computing, the idea is that the startup now doesn't really buy fixed costs, right? It doesn't have hardware. It just goes to the cloud and swipes essentially the credit card and gets access to more IT resources. And as you know, the number of users or the number of CPUs, this all determines how much variable costs you have, but you can always scale down and up. So in a way, you, of course, have not this fixed cost in capital, which is on the one hand a bit misleading because here is a rough cut. Usually would have a lifetime of 4 to 5 years, and you have to renew that thing, right? While you don't renew here anything. This is done for you. You don't ask Amazon, please exchange my CPUs, please, they're out, or something like this. When you bought it once, Your trouble is after 2-3 years, you have to think about an upgrade or basically new hardware to buy. So all of this fixed cost will remain and maybe going bigger. And the staff has maybe to change the technology and learn new things. So this is really an idea why cloud computing could be beneficial. What's a bit unfair, I think, in this comparison is, and this is out of a book, is that sometimes the variable cost is a little bit more exponential, right? Think about our worker, Spark. Yeah, when I have a little bit of, one Spark cluster here with 2 workers, I'm here. But when I want to have 60 or 80 workers, then of course the variable costs in, renting this model is essentially getting very quickly very much up. So it's a bit more exponential than really that. But of course, when you look on the traditional model, you can argue that people don't have to train on the technology that you bought here. That's a good argument. So you reduce again the curve. So in a way, it's accepted to put it that way in a very rough, form. But of course, when you now move into this, there are nuances. That's why you have so many resource classes. We see in lecture 8, when we do infrastructure as a service, alone on this, just buying bare metal, hardware, storage, we have so many choices that determine this one. That of course there, the interesting thing is to put it also in the equation of this. You have much more capability here, much more options. Here you're very, very, very fixed to one specific equipment you buy, which might be not always the best for all. So again, it's an idea how you would now justify to your boss. Should we really have a server in our house, or should we go to the cloud, right? So this is one of the key questions, of course, which is today in kind of companies, in SMEs, in small startups. Good for a startup to start is maybe always renting, but quickly you have like Angry Birds and suddenly exponential amount of users. You could go there and pay the price for it. What this shows it a little bit in this is exactly this exponential curve where you say, this is quite a benefit, because when you have this kind of logical servers that are essentially more or less installed, which are not really existing, we call that logical service, and then the line to the physical service. You have the so-called virtualization management gap, where you see essentially then the benefit rolls really out if you have the so-called economics of scale. So if you go that far, it is not good for you to just do it for a couple of servers. Then maybe it's even better to do it at home. But if you have it, and create a data center yourself, then really the key benefits become, when you go bigger, employ lots of virtualization, and then of course have, let's say, through this virtualization, really lots of benefits. And this is a term we will also coin more and more when we think about the metrics that we will have. Also, another element is you see here, the cooling is 33%, but we also have to take the emergency power into account, right? Air conditioning is again part of the infrastructure. So you basically come to a conclusion that lots of money goes also not only in the server, but to the environment that you have essentially around it. So, and this is, of course, now think about the environment now, and you have a very tiny data center doing all the same thing, preparing it instead of having it as a large data center, which has then this economics of scale. So in a way, you can conclude with this, what we just said, also maybe making the electricity cost of the servers playing into the game with all the percentages, you come to a very important note that 60% cost of the data center costs are indeed just management, maintenance, the surroundings. So the servers in itself, the infrastructure itself is computing doesn't cost so much, and the storage and networking, but everything around it of the data center is, of course, a key consideration. So, and from power efficiency, just the point of view that this is a little bit changed in the terms of GPU usage. You have seen CPUs are basically very high single threaded, so they need lots of energy for their heartbeats and single thread precision, and really high frequency really of the CPUs. But we have also seen there's an end, so more and more GPUs coming there. GPUs, on the other hand, have not this high frequency. They have thousands of moderate processors, and with this all that framework together, they're actually quite energy efficient. So GPU is, in a way, if you want, a green way of doing computing. And with this, you have much more, let's say, options around more energy friendliness. But we also have seen that, of course, the GPUs in one of the earlier lectures, lecture 1, lecture 2, are limited in the applications. You cannot do everything with a GPU. So that's why you basically use still the CPUs. But it's really, again, then, of course, per what scenarios, what application loads you have in terms of what you need, what you can do. Just take away the measures that usually the GPU is much more, optimized for energy efficiency. And that's one of the reasons why more and more servers today are also more energy efficient, because they have this GPUs on board. And they're getting better and better in this, essentially, what you can get out, so to speak, on a flop per energy. Now, coming again to this economics of scale, it's a very interesting word in the end. Just think about that there is some benefit if you scale up. And this is with the large, hyper installations here. You see Microsoft Cloud Computing Center. They have 100 data centers of this form, which fill many, many different football fields. Because if you have the infrastructure rights, you have the diesel generators right for emergency, you have the cooling infrastructure right. The real benefits of operating this is this economics of scale of just having not 100 server, you have thousands of them inside a data center. Even if you would argue now, then if you have thousands, there's a failure almost always, and you need more crew. Still, there's a, let's say, very easy going of having just one guy going through this and changing more hardwares than basically having everywhere separately a small data center and always having staff for all its different things. So this kind of conveys a message that just by having this large data centers, you can see that the storage costs, for instance, here with 1,000 servers is about 5 to 7 times greater when you basically have a small data center, just because you can basically rule out so many informations that basically is there for a small data center. You can operate a scenario of deployment with changing hardware all the time, which is a key issue there. You have the cooling infrastructure. Once cooled, you basically have a larger room cooled is okay. There are lots of these economics and scale that are really measured these days and given as a performance indicator. Here's an example of hosting 400,000 to 1 million servers, right? So this is how the big operators actually do this, and that's how they can actually then afford, let's say, a CPU for a couple of cents to give out. And there are many of those centers. Now, the question is, what happens if they fail? What happens, how they actually basically constructed together, how you created such a big piece we have just seen in the picture. So the smallest entity would be always a server, but this is not directly a cloud thing. Many things have a server, so maybe you have a file server at home. So that's not a big thing. As soon as you start then suddenly to have this kind of clusters of servers, you basically have this multiple servers idea. So you have really different servers, but of course, don't think about that. You not start and do all of these and put them together, let's say, as boxes. You have highly optimized racks today. That's the next entity. The racks are specifically cooled with a good design. They're very well interconnected. So I have a network part. And in a way, they have really a very dense part, how to put CPUs in so that you don't waste too much space, right? If you have 1 million servers, like you have seen in this huge data center from Google or Facebook, then you don't want to waste space. You want to put more and more in. That's why the rack is a very condensed space to have basically all parts in. And then you just add up adding racks and racks and racks. As you see in this picture here from a Google data center, all these different pipes is what I also mean in terms of the maintenance, in terms of the infrastructure. You have to see that those systems partly are today water cooled, or essentially a very specific fire system there. So of course, obviously a big server farm with 1 million servers, you don't want to have a fire system which basically turns out a fire with water, right? Because when you have electricity running all the way and there's a fire somewhere and you put water in it, then you do more damage. Hence, you have usually something like a gas infrastructure, argon gas or some specific gases that actually turn out the fire. This infrastructure costs, but if you just have it already in place, all of this, then it's not a problem of adding another football field and another football field. It added a bit for the place, but the infrastructure is almost there. So, and of course, for this, let's say more football fields, you get more users, more return of investment. This is the economics of scale. But the data center is also not just putting rack by rack by rack. What you don't see in this picture, for instance, there are usually second floors underneath where all the network cables are. I come to this in a moment. And where let's see, the circulation of heat, which plays a big role, is really fundamentally, let's say, put into the infrastructure design, right? And of course, then you think about, you have more of those data centers. What happens with a power crash? And of course, you have replications of data in different ones. That is all adding up to the idea that when you swipe the credit card, you have 99.7% that the server works, because they actually can always employ them on different zones. They can employ them through replication if you have different storage. So this is, of course, a key element of it. But also there in these big centers, errors happen all the time. Now, when there's, let's say, a power crash, I mean, some of you know that someone has to go to Bolungarvik. They have just a recent big, installation of these diesel generators, right? Because the power lines go over the mountain, and in bad weather, you cut from Isafjorda, and then, ouch, no power, right? And then you see at your iPad, oh, suddenly 5, 4, 3, 2, no loading. So they have a new power station from Landsnet, essentially, that has also 4 or 3 of these diesel generators. And the same way how it works essentially for the power lines here in Iceland and the smaller cities and so on around the countries, that is what you do with a data center, right? Of course, this has several side effects. If you have a very large system with many different football fields, you need also many of those to keep it operational for a very long time. But usually they are also just employed for a couple of hours to find the errors, to find the problems, or to give chance to migrate the current workload to another center that works. But these kind of UPS are usually very helpful in at least dramatically reduce a problem when there's a power outage. And it is in the recent years less and less, right? So of course, something which still the cloud providers have to address, because essentially you've swiped your credit card for 99.7% performance. And if they suddenly say to you, well, actually, we have no power in one of the data centers, sorry, then of course you want your money back because you said it's 99.7. So this is a very important ingredient. It gets less and less important because the sizes are just so incredible these days that you need hell a lot of diesel generators to help it. Plus all the problem of, having diesel always there and so forth. But still, you see many of these data centers have still diesel generators alongside. Now talking about, as I said earlier, the idea of the second floor of the air circulation. So a big data center that you create is not just flat. Usually a key consideration, hence what I told you about the cooling infrastructure, is a very important part of it. So the air circulation is basically directly related to the cooling. You can imagine that cool air coming in will be very quickly heated up when they move through a rack, because here are not just, let's say, a normal laptop operating. Here are, let's say, just a number, 1,000 laptops on a very condensed space working together, right? Imagine it this way, 1,000 servers, and then suddenly, of course, the heat goes dramatically up. So that's why essentially the idea of working and operating and getting then maybe something like you see here, it will be cooled down again, either to ambient air channels outside. That would be one idea. Some have actually liquid coolings. It doesn't matter, but the idea of this would be very important. And when you go to a data center, and we go to Vern and others, you will always see the floor has sometimes interesting different look and feels. And this is because of the air circulation through it, right? So some of them, of course, are very proper for the racks. Then you see normally lots of energy or network cables around here, which fills the second floor. Sometimes you see other elements in it, like even also the protection against fire. So it's a very typical way of doing these data centers, and something which you usually don't see, because the beautiful pictures usually show also only, the floor on top and never the second story. Then, of course, the internet is also one part of it, or the network infrastructure. If you want, there's also redundancy many times. You see essentially every now and then could actually a complete switch failing. And it still needs to be possible to have, let's say, the data center operated. That's why the network that you see on the rack is, of course, not directly centralized to all, let's say, network connection. So you would have a very high, basically, distribution of the network functionality of many different switches, so that you have also multiple connected server nodes and racks that you see a little bit here illustrated with these pictures. And with this, of course, it makes sense to think about migration of virtualization that we had before very early. If you see that the network connection boils down and so on in the monitoring. And then suddenly, essentially, the switch fails. You have perhaps already started to migrate away the application so that this hurting the network will not really, disturbs you. Alternatively, we learned about Spark. When Spark was running partly here and it remembers the submission and it can connect anymore, it will actually resubmit it somewhere else on the Spark cluster to actually automatically deal with the so-called faults and errors and failures that we can assume essentially in these systems all the time. So this is more the kind of fat tree switch network. Yeah, there's a question in class. Though the question is why it's called a fat tree, and this alludes to the oversubscription of the network channels that you have here. So essentially, you can have also another tree infrastructure where you not have, let's say, everyone with everyone more times. You would save network cables and assuming an oversubscription of users, because essentially what we see here is very expensive. A fat tree refers to lots of real physical connections. And when you have a big installation of a computing entity, firstly, not everybody's using extensively the network. And secondly, if you go to look to a big data center, that's essentially one of the most expensive things, the network. If you look at our systems from HPC, from clouds, the computing is cheap. The storage in a way is cheap. Of course, memory and so on is a bit more expensive, but in the end, connecting all those together with this end to the infinity of cables is one of the most expensive things. That's why in newer elements, you have things like Dragonfly. This is something what I teach in HPC rather than here, but it's also a very good question. So this is more the fat tree topology, saying you have always different lines that can be, re-exchange. With this, you have better fault tolerance, of course, right? When you have more lines really existing, it's easier if one falls apart, you can just use the other line. If you don't have a fat tree and you have, let's say, another idea that you're running your data center with less cables, then you come into the trouble that essentially if there's a fault at some point in time, you maybe not really can good deal with it. So you see all the applications will have to carry the load. In this example, you see that basically every server is still very much connected, except those that dropped out with all the other ones, except of having, let's say, going always through one centralized one or so and then distribute. Very good question. You should go to my HPC course. So there we do actually much more on these interconnections, right? Which is more on the lower level. There are lots of tricks, as I said, as oversubscription, assuming that users will not use so much network load, you can steer that and so forth. So that's a very good question. It refers to an operating aspect of the data center. Of course, there are people all the time monitoring the data center. How much is this used? Here you have something which is a little bit also a change of thinking, hopefully, when you think about a big data center. Many of you maybe have this in mind now, a big pile of storages of, typical hard disks that you have to put somewhere in your desktop computer or that you have even in your laptop. But how you do it normally is in a big data center, you would have something like a NAS, also really an array of storage disks, right? That are also, again, very condensed, very close to each other, running so-called RAID strategies for data loss and so on. All things we do a bit more in the HPC course because they go a bit more lower level than the high level cloud course, right? Which is a bit more user oriented. And in the end, you have then this combination possible. Of course, as a client host, you would then transfer the data. It look and feels almost like the same you have already on your own laptop. But essentially, it is running in a very redundant space in this disk arrays, maybe with replication strategies across data centers to mirror the data all the time. And with this, a very safe way of storing data. But the game, as soon as it is in the cloud, also storage costs, not only GPUs, CPUs, storage as well. Some metrics for scalability. I think here is just the idea of revisiting a bit the scalability that you have heard in the video that I'm always talking about. This is a key word in cloud computing, right? One of the main motivators, but there can be different angles to it. So you would say size scalability, which is, I think, for everyone very obvious directly, is that you just have more CPUs, you have more GPUs, you have more power of I/O channels and so on, add more storage. That's something what everybody can essentially directly refer to. Of course, here we have also then the idea of clouds of software scalability. So you can say that you run different applications in different, let's say, servers, maybe you have a big programming team, so they get more services than just basically a little kind of cluster that has, let's say, the idea of administration of employees and so forth. So you can have different versions of different software in parallel. MATLAB new version, MATLAB old version, because some prefer the old version, some prefer the new version. All possible is virtualization. So all of these are basically scalability options that you can put in, which is very important for you if you are in a company. And then you would have application scalability, of course, thinking about that there are many different workloads in the cloud. The applications you essentially would have in terms of problem size. Again, you do machine learning with logistic regression on 100 megabytes. And here application scales just using Apache Spark cluster, and we use a 100 terabyte. Nothing changes from the code, right? The Spark clusters automatically will scale to 30 workers that you of course have to configure, but the application itself, the SGD, everything we learned will still scale up to these different workers. And technology scalability in the end, using different components from different vendors, becomes very obvious very soon now with the move to more better GPUs, right? From Kepler to Volta. Now we have Ampere and so on. So unbelievable changes in GPU speed. And you can do this, let's say, in a scalable fashion. Some part of the virtual cluster has just this amount of GPUs and the others have, a newer version of the GPU, but it's really technology and abstract away from the user. Finally, I just want to brief you again on this hybrid and public cloud. So public cloud is very obvious to use, is Amazon. That is something like MS Azure. Private clouds is usually something we learn then later when you create it yourself is OpenStack. And the reason could be data protection, that you don't want to put it in US clouds. So we will talk about these topics intensively in 8, 9, and 10, just for you a glimpse how it works. And of course, hybrid means you connect both. You do these public data things, which you can put in, more public spaces, work on those, while medical data or something very sensitive, you maybe keep in your own company. Good, but as I said, we will talk about this extensively in 8, 9, 10. So here just a sneak preview. I brought with you a video, and while you maybe can also leave for next course, so don't worry, it will be on the YouTube lecture. Just it carries a nice essence of essentially how a Google Center looks like. I play it here for basically the YouTube and remote audience, but feel free to look it also on YouTube if you want.
Internet, the engine of the internet.
Hey, bye-bye.
It is a giant building with a lot of power, a lot of cooling, and a lot of computers.
It's row upon row upon row of machines, all working together to provide the services that make Google function.
I love building and operating data centers. I'm Joe Cava, Vice President of Data Centers at Google. I'm responsible for managing the teams globally that design, build, and operate Google's data centers. We're also responsible for the environmental health and safety, sustainability, and carbon offsets for our data centers. This data center here in South Carolina is one node in a larger network of data centers all over the world. Of all the employees at Google, a very, very small percentage of those employees are authorized to even enter a data center campus. The men and women that run these data centers and keep them up 24 hours a day, 7 days a week, they are incredibly passionate about what they're doing.
In layman's terms, what do I do here?
I typically refer to myself as the herder of cats.
And I'm an engineer, hardware site operations manager.
We keep the lights on, and we enjoy doing it.
And they work very hard. So we like to provide them a fun environment where they can also play hard as well.
We just went past the 3 million man-hour mark for zero lost time incidents. 3 million man-hours is a really long time, and with the number of people that we have on site, that is an amazing accomplishment.
I think the Google data centers really can offer a level of security that almost no other company can match. We have an information security team that is truly second to none. You have the expression, they wrote the book on that. Well, there are many of our information security team members that have really written the books on best practices in information security. Protecting the security and the privacy of our users' information is our foremost design criteria. We use various layers of higher level security the closer into the center of the campus you get. So just to enter this campus, my badge had to be on a pre-authorized access list. Then to come into the building, that was another level of security. To get into the secure corridor, which leads to the data center, that's a higher level of security. And the data center and the networking rooms are the highest level of security. And the technologies we use are different. Like for instance, in our highest level areas, we even use underfloor intrusion detection via laser beams. So I'm going to demonstrate going into the secure corridor now. One, I have to be on the authorized list with my badge. And then two, I use a biometric iris scanner to verify that it truly is me. Okay, here we are on the data center floor. The first thing that I notice is that it's a little warm in here. It's about 80 degrees Fahrenheit. Google runs our data centers warmer than most because it helps with the efficiency. You'll notice that we have overhead power distribution. Coming from the outside yard, we bring in the high voltage power, distribute across the bus bars to all of the customized bus taps that are basically plugs where we plug in all the extension cords. All of our racks don't really look like a traditional server rack. These are custom designed and built for Google so that we can optimize the servers for hyper efficiency and high performance computing. It's true that sometimes drives fail and we have to replace them to upgrade them because maybe they're just no longer efficient to run. We have a very thorough end-to-end chain of custody process for managing those drives from the time that they're checked out to the server till they're brought to an ultra-secure cage where they're erased and crushed if necessary. So any drive that can't be verified as 100% clean, we crush it first, and then we take it to an industrial wood chipper where it's shredded into these little pieces like this. In the time that I've been at Google for almost 6.5 years now, we have changed our cooling technologies at least 5 times. Most data centers have air conditioning units along the perimeter walls that force cold air under the floor that then raises up in front of the servers and cools the servers. In our solution, we take the server racks and we butt it right up against our air conditioning unit. We just use cool water flowing through those copper coils that you see there. So the hot air from the servers is contained in that hot aisle. It raises up, passes across those coils where the heat from the air transfers to the water in those coils, and then that warm water is then brought outside the data center to our cooling plant where it is cooled down through our cooling towers and returned back to the data center, and that process just repeats over and over again. To me, the thing that amazes me about Google in the data centers is the pace of innovation and always challenging the way we're doing things. So when people say that innovation in a certain area is done, that we've kind of reached the pinnacle of what can be achieved, I just laugh.
Yeah, thank you. So that's all for today, and we continue with our lecture 5 on Thursday.